start again, and this time there will be, the voice will be recorded. All right, so are there any questions? Should we go over the set test questions and whatnot? I spend a lot of time to make these questions, okay, so that it is cut, so that there's like a 30 set of different questions, and then you just get multiple on each, for each person it's kind of be. I do not like Canvas at all. A lot of stuff, that should work, in a much more streamlined way, it does not. Canvas probably is really great for professors who use textbook modules. Okay, so they can just purchase the module, or people purchase the textbook, and then the publisher supplies the module that plugs into Canvas. So all the activities will come with the textbook. But then you guys will have to pay like $200 for that textbook.
Did you fix the issue from yesterday?
Yes. So the Monday, Wednesday class in assembly should be fine. That issue is, yeah. So the problem with that issue, once again, it's something that I really do not like about Canvas, is if I make several copies from one single question, they become completely independent. They become objects, basically. So the questions in a test bank is more like a class. So when you put a quiz into if you put a question into an actual quiz from a test bank, it becomes an object. So if you redefine the class, the object doesn't change at all. So the object is completely independent to the class once it is manufactured. So fixing the class doesn't do a single thing, to the objects. And Canvas does not let me regrade automatically, submitted answers and say, okay, these are the new equations and this is how we figure out the answer. It would not let me regrade, so I'm gonna have to grade all that stuff manually, which I'm procrastinating.
Oh, okay, so that's why it says still working on it and there's nothing happening.
Okay, so question number 1 is asking which of the following is true. Okay, now since it's a bubble or it's a radio button, that means only one and only one is the correct answer. Okay, so uppercase A has lowercase a, b as elements. Uppercase B has a, b, and c lowercase as elements. So the correct answer is A is a subset of B. Okay, so that should be it. All right, moving on. So question number 2 is one that I have to grade manually, but I will give you the answer to this one too. So given that A union B is A, B, C, D, E as elements, A minus B, or the difference between A and B, is CE, define a membership arrangement of the sets A and B to satisfy the constraints. Enter your answer in the HTML editor area. Be sure to use all correct notations. Okay, so what I'm really looking for is something simple, like A, or for those of you who like to do it right, then you use the equation editor. Okay. Yep. So we know that C and E are in A, but not in B, because their B is A minus B. So we're going to put those two here. Okay? Now, the other thing we also know is the union has A, B, C, D, E. So in order for A to at least have C and E, and B has, the union of these two has A, B, C, D, E, B is going to have A, B, and D. So let me insert the equation. That would be the correct answer. Any other questions about this? Okay, we got many questions, so I'm going to go from left to right. Yeah, go ahead.
Since the subtraction is defined as like the elements that are in A and not in B,
yep.
Would it be fine for A to contain every element as long as B contains A, B?
Yes. So A can be A, B, C, D, E. So as long as B does not have C and E, that would be fine. So there are, okay, so let me ask you this question then. Okay, how many possible answers do we have for this particular question? Now that we know that A can be A, B, C, D, E, or just CE. These are the two extremes. So how many answers are quote unquote in between? 8 is correct. Actually, it is not. Is it 8? Yeah, it's just 8. Okay, because for the elements A, B, and D, they can be present or absent in A, and it would not affect the correctness of the answer. So because A can be there, can be missing, B can be there, it can be missing, D can be there or missing. So now we have 2 times 2 times 2 ways to arrange set A so that it still becomes a valid answer. Okay, there were a few other hands. Yep, go ahead.
I was gonna say, what's up when we wrote it what's up if you wrote it backwards? Cause I accidentally put in the A equals A, B, and D.
You can write it backwards. You can say A equals, or you can put B ahead of A if you want to.
Yeah, but why was you see where the B is? I had the A there because I misread the instructions. So mine says A equals A, B, and D without the B with the C and E, because I did not know if you wanted to be written like that. So
that would be incorrect. If uppercase A has any one of these, it would still be okay. The key is A has to have at least C and E. It cannot miss C or E, but it can have any additional elements that you want to put in. Any other questions? Oh, okay. So a lot of the questions are duplicate. Okay. I like those questions. Okay, number 3, choose the correct answer. Is A by itself an element of a set where the only element of that set is itself a set of A? The answer is no, it is false. Okay.
My computer lagged and I accidentally hit true. Can I fix that? My computer lagged and I thought I hit false on that, but it can't turn out to be true. Once I hit true, and I thought I clicked false, but my computer lagged.
This is not League of Legends. You cannot use lag time.
No, I'm not lagging because I was in the face of all when I tried to.
Now, of course, League of Legends, it's not that time sensitive. But if you're playing CS:GO, you go like, I'm off by 5 milliseconds, and that's why I'm missing that shot. I mean, come on. CS:GO does not take into consideration, trajectory, bullet drop, wind, and anything like that. It is not realistic to begin with. So for any one of you who want to be, I think I can do this. Okay, I can take all of those things into consideration. I'll meet you in the next airgun field target match.
Oh, you do metal airsoft?
Huh?
You do metal airsoft?
It's not airsoft. It's pelicans.
Okay.
Very different. Airsoft, you can probably, have, a range, but you have no idea what you're going to hit. you see that plastic ball going like, woo, woo, like that. Okay, question number 4. Choose the correct answer. Again, is the set of ABC a subset of the set ABC?
Yes.
It is, okay, because this is not proper subset. If I change this to proper subset, then the answer will be false. But since it is just regular subset of, the answer is true. Okay, next one, question number 5. The union of the set that contains elements A, B, C and the set that only contains A, B is ABC.
Yes.
That is correct, because we do not repeat elements in a set. Question number 6. Regardless of the definitions of set A and B. Now this is really important. It means it doesn't matter how I define set A and set B. Okay? Is the following always true? That is what it's asking. Okay? So what is it asking? It's saying that A minus B is an empty set, which means everything in A is in B. Okay? There's nothing in A that is not in B. Okay? Does that imply A is a subset of B is false. Now this time it is a proper subset, okay? A is a proper subset of B.
I think this one might have false.
Is it always true, or can you find cases where it can be false? What do you think? What is the definition of subset of?
It's every element except every element in A can be found in B.
Every element of A can be found in B. So this is just subset of, right? If it is a subset of, can we say it is not a proper subset of? Does it automatically imply?
No.
It does not automatically imply. So the answer should be false, but I may be phrasing it, in a way that is kind of confusing. But it's definitely not always true. Okay? Because I can find cases, I can define A and B so that this is false. Yes. If you make A actually a subset of B, it will make this part true, but it will make this part false. True implies false itself is false. You're done. Okay, let me explain that. It was on my tablet. Give me a second to start that up. Uh-oh. There we go. Okay, so if I define A to be the set of AB, define B to be the set of ABC, okay? So now the question is the first part or the left-hand side of the implication true? Okay, so let's figure that out. A minus B is an empty set. Is that true or not?
Yes.
It is true. Everything in A is indeed in B, so I cannot find anything that is in A but not in B, which is what A minus B is trying to find. So this part is true. Okay, so we say that's true, and then we try to figure out the second side. The second side is saying, is A not a proper subset of B? Well, A is in fact a proper subset of B because B contains more elements than A. Okay, so this is true. Not true is false. So now you have true implies false, and that implication is false. Because implication itself is the negation of the first part or the second part. So is that okay? Yep.
What if A would be ABC as well?
If set A is ABC, then A minus B is an empty set is still true, but this part is true as well. So because in that case A is not a proper subset of B, so that means the second part is true as well. But the question is asking, regardless of the way I define A and B,
That's how I got confused.
yep, for all A and for all B. So next time I'll use the for all quantifier. Okay, so question number 7 is kind of the same thing. It's saying for all A and for all B, uppercase A and B, if the union and the intersection of AB are the same, does that imply A equals B? The answer is true. Very good.
I told you I'm studying. I lagged on the last question. I was like, oh, Professor Tackett, I believe in you. I just lagged.
It just takes longer if you slide, right? Okay. Unless you're using the keyboard to scroll through the question and then use another hand to click. So in that case, your lag can actually affect your aim, right? It's like a moving target. Yeah. Or you can, if you have a brother or something, you know, you can have a fun game. Your brother will be rolling it up and down randomly, and then you'll be the one trying to click the right answer, right? It's called a poor man's CSGO. Okay, regardless of the definitions of set A and B, for all A and for all B, if I say that A is an element of B, okay, the set A is an element of the set B, does that imply A is a subset of B is not true? Or it is not the case that A is a subset of B? Is that implication always true, regardless of how we imply A and B? Okay, I'll give you the answer. The answer is false.
Yes.
Okay. So are we doing okay so far with all this? Yes? Go ahead. Go back to number 5. Okay. Okay, there you go. All right. So are we good? Okay. All right. All right. So when this is all done, we're going to go back to all the modules, and you do have a new homework assignment. Your new homework assignment is on functions. So that will be under the functions module heading, and it's this one function assignment. You have 1 week to work on it. So it's due on Valentine's Day. Yep. Does it not show your answer anymore? How about now? Does it show it now? Now that the test is actually over?
I think you just checked. No.
Oh, it still does not show? Okay, I'll fix that.
No, I actually did. Like when the test was, it did
Going?
show the answers, and
Okay.
after the due date, it stopped.
Okay, so I can fix that. Maybe after the class.
Okay.
All right. So we are done with relations. Okay, that's the topic on Monday. Are there any questions about relations? So there are many aspects of relations that we talk about. We talked about reflexivity. You know, is a relation reflexive? Which means for every element in the set that a relation is defined over, is each element relating to itself. That's reflexive. The second one is symmetry. Okay, symmetry means, you know, if A are B, if and only if B are A. If one is there, the other one has to be there. If one is missing, the other one has to be missing. So the empty set of the empty relation turns out to be not reflexive, but it is symmetric. Okay? In other words, empty space has symmetry. Kind of makes sense, right? Yes?
I was going to say, I do have some questions about relations, but I was going to tell you this is going to be after class. So
Okay.
make sure that I took down a lot of notes on them. Make sure they're correct. That's it.
Okay. So the next one is yeah, go ahead.
So empty space is also anti-symmetric?
Empty space is also anti-symmetric, and it is also automatically transitive. So what is transitive? What type of relation is transitive? ARB and BRC implies ARC, right? That's it. But an empty relation is automatically transitive because you cannot meet the requirements on the left-hand side of the implication. So that side is always false. If that side is always false, then it doesn't matter. The whole implication is true. All right. And then we have anti-symmetry. What is anti-symmetry? ARB and BRA implies A equals B. Okay, that's anti-symmetry, which is kind of misleading. And then we define partial ordering as well as total ordering. So is that okay so far, those concepts? We used the beer commercial to illustrate partial ordering, right?
Yeah, smooth, not rich. I like the smooth that it wasn't rich.
Yeah.
He's thinking smart.
That commercial was really funny. It's, by the way, I think it was an Australian beer also. Yep. That's why the humor is a little bit off. I think it has to do with crossing the equator. Somehow all the jokes, that passes the equator doesn't work that well on the other side.
They're all upside down.
The spin is different. All right, so that's relations. So we are moving on to Aleph null. Do we have any questions back there? We all good? Okay. Yep, go ahead. The first exam is going to be about week 5. I think we are in between week 3 and 4 at this point. Is it 4 already? So maybe next week we'll go over a practice test, and then the week after that we can get a first test.
Man, that test looked complicated, Professor. I saw it.
You saw?
Yeah, it looked like a whole nother different language.
Okay. Well, same language as in the class. Yep.
Everyone exam the same day as like the instructors. Most of us are in that class, which we go into move the exam around.
What day do you have it on their structure? I mean, I cannot evade every other midterm because there's always somebody's going to have a midterm somewhere in some class. So I can evade the most popular or the one that conflicts with most
which would be
people in the class.
He'll tell us today.
I mean, somebody may be taking funeral service and they end up with a class, a midterm on that day. That requires a field trip. We are one of the very few colleges that actually offer funeral service as a certificate and a degree. Did you know that?
Say it again.
We are one of the very few colleges that offers funeral service as a program. And guess what? Compared to development, computer science and stuff like that, nobody's going to outsource funeral service.
That's true.
It's not going to go overseas. Think about that.
Unless we.
And they're always customers.
That is too blunt.
There's always customer in funeral service. Okay, so think about it. People may not, people may refrain from playing video games, but they always die.
You can't restrain death.
As it turns out, funeral service actually has a lot of regulations and whatnot too.
Oh, okay.
You cannot just say, "Oh, I'm going to get cremated and spread my ashes wherever I want." There are regulations that says that you cannot do that. The EPA, the Cal EPA, actually has regulations of where you cannot spread your ashes for environmental impact issues.
Oh, wow.
Yeah.
The Pacific Ocean is so big. There's like dead bodies in there all the time.
Okay, so we're going to move on to Aleph null. Okay. Okay, so are you guys okay back there? Okay, because I just don't want, if you guys had a cone of silence on top of you, I wouldn't really mind at all. but since we don't have that technology,
All right, working on it, Tag.
working on it,
Yep.
cone of silence.
Yep.
All right, so we first consider the set of all natural numbers. Okay, so do we have any questions about what natural numbers are? They are, go ahead.
-1, 2, 3, or just regular 1, 2 through infinite, or like try to review because it's been a while.
See, these days, as a professor, I don't have to know anything because I can just look it up. Okay, so let's find out what are natural numbers, right? But when I do this, I'm also telling you that you can do that too, because Google does not have a. It doesn't need authentication. You don't have to be a professor to sign in and search for these things, right? Okay, so in this case, natural numbers is defined as the positive integers, and sometimes 0 as well. So that's the fuzzy part, okay? Whether it includes 0 or not, the way we use natural numbers really doesn't matter, okay? But for discussion purposes, we'll just say that it does include 0 in the set of natural numbers. That's how I was taught, but there were some people who were taught, natural numbers do not include 0. I mean, off by 1 is not really that big of a deal when it comes to mathematical concepts.
So how would we deal with another professor that debates it? Like, do we just ignore it and just go on with it, and then?
Well, it becomes whichever class you take. Okay, if the professor says in this class natural numbers start with 1, then you use that definition in that class.
Right, but then what about the workforce? If your boss says it, and then you got to program the satellite, make sure that thing don't crash.
Then you ask your boss, what do you mean by natural numbers? Because there are 2 ways to interpret natural numbers.
All right.
You ask for clarification.
All right.
But that's why communication is important. That's a soft skill that employers look for. Okay, so that's the wrong note. Yeah, right here. Okay, there we go. Okay. The cardinality of the set of natural number seems to be infinity, but that's not how we look at it. Okay, so what we do is we make this definition. This is by definition. This is how we define aleph null. Okay, the kind of wiggly end is aleph, which I think is from Hebrew. Is it Hebrew? Okay, so it's a Hebrew letter, aleph. Aleph null is by definition the cardinality of the set of natural numbers. Is that okay? It's just a definition. Is that okay? Any questions at this point? No questions? All right. So now.
Oh, I do. So that's all. So that symbol just means just natural numbers.
Which symbol?
The N and the
This N is the set of all natural numbers.
Right.
The bar says we are only interested in the cardinality.
Right.
And then this is aleph null.
What page for it?
ALEPH. So look it up. So ALEPH is aleph, and then if you say null, that should get you discussions of that thing. Aleph null or aleph 0. Same thing.
That's where it's German. There was a lot of Jews in Germany. That's why it's German term.
So that's just
But I think they chose this symbol because it looks like N.
Yeah, that makes sense.
Okay, so, but that's just the definition. That's just how we define aleph null as a symbol. Section 3 talks about equivalent cardinality. In other words, how do we compare the cardinality of 2 sets? Each one has, quote unquote, an infinite number of elements. Okay? So, in other words, how do we compare the set of all integers as opposed to the cardinality of all natural numbers? That's what we are trying to do. Okay? So for the most part, we want to say, are they the same? Okay? Because the one really good question is, are they the same? Is the cardinality of the set of integers the same as the cardinality of the set of all natural numbers? That is the question. But how do we compare? It's infinite, right? So naturally, most people, no pun intended, so naturally most people think the set of integers is bigger than the set of all natural numbers. There's no one-to-one mapping. If you think about it, people think, hey, if you use the subset notation, the set of natural numbers is a subset of the set of integers. You give me any natural number, it is automatically an integer. But if you give me an integer, like a negative value, it is not a natural number. So it meets that requirement of a subset of, proper subset in this case. But interestingly, when you look at the cardinality, they turn out to be the same. That is weird, right? Yep.
I was gonna say, with computer representation, when you do an int versus an unsigned, you can't represent it with bigger numbers. They'll have the same range, but one is in the positive.
Are you talking about fixed width integers?
Well,
If it's fixed width, then you have then unsigned has more positive values that it can represent. So when you look at the number of integers that can be represented, it's the same whether it's signed or unsigned. Yeah, you're just shifting that range so that it is either centered at 0 or it starts at 0. That's the only difference when you have fixed width.
I was
Okay.
thinking if you make that as cardinality, it will be the same.
That is correct. When you have fixed width, then the cardinality, it's easy to show that the cardinality is the same. But when you do not have a width requirement, then it becomes much harder to make that statement. Yep.
Could you just remind me real quick what the cardinality is? I remember it's like the total amount of elements, but there's like an issue to it I don't remember.
It is the number of elements of. It's the count of number of elements.
The total count of elements.
Right. So that's cardinality. Okay. So now I need to somehow show you guys that the cardinality of integers is the same as the cardinality of natural numbers, which by definition is aleph null. How do we show that? How do we show that two sets, each one has an infinite number of elements are the same? They have the same cardinality. So what we're going to do is we'll define a function. So this is function f. It is defined to map z to n. In other words, the set of all integers is the domain. The set of all natural numbers is the codomain. And f is going to make this map from z to n. Okay? So the way I define the function is right here. Okay? And it makes use of the ternary operator. That makes this class a computer science class and not a math class. Because no math professor is going to use a ternary operator.
Except for that one guy I know. Except for that one guy I know.
There's one?
Yeah, there's one. He said city though, but he uses it.
If that person is on this campus, I would suspect it's Phil Smith. Because Phil actually programs in PHP, and PHP does have a ternary operator. Okay, so does everybody understand what is a ternary operator and how it is used? It's an if then else, right? This is the condition, this is the then value, this is the else value. Is that okay?
So you take the function.
So the first thing you have to do is to evaluate the first part. The first part is f of x. Okay, so our parameter is x. So the first thing you need to do is to ask, is x greater than or equal to 0? If the answer is yes, then the answer to this question, or the f of x, is 2x, which is guaranteed to be an even number. Okay? On the other hand, if x is greater than or equal to 0 is false, x is less than 0, right? So if x is negative, then we use this formula instead. It's minus 2x plus 1. Okay? Now because we start with negative 1, the negation of 2 times negative 1 is 2. 2 plus 1 is 3. We are doing it off by 1.
Yeah, it's giving an odd number.
It's not odd number, but we are off by 1. I want it to be, I think it's supposed to be minus 1, not plus 1. Let me see if I can fix that. The issue of not being able to sign into my home server, I boiled down everything to a DNS issue. For some reason I cannot, the DNS server setup on this campus does not let me see ddns.net for some really strange reason. So you might say, well, maybe TAC, it is just how you set up your own computer. I can assure you that is not the case. So let me sign into another server that is just a typical Debian server, nothing really special. It's running on AWS, the Amazon Web Service. Okay, so it's really run-of-the-mill, a Debian box. And on this machine,
You're really running this off of an Amazon server?
Yeah.
Oh.
This one, this machine here, the one that I just signed in. See, with this one, I can see ddns.net. If I can see ddns.net, then I can actually sign into my own server. But I have to bounce off another computer first before I can sign into my own computer at home.
This is some more watchdog stuff.
Watchdog?
Yes.
Where? Oh.
And the first achievement you get is called Hello World.
Okay, so we go to modules, and which one is that? It's module 293, so we go to 0293. And we are looking for, I'm just looking for a phrase that makes it easy to find it. Minus 2x plus 1 should do, right? Minus 2x plus 1, right there. Okay. Change that to a minus right there. And by the way, this is all written in LaTeX. It's technically LA, but not TEX. It's LA tau epsilon chi. So it's not pronounced latex. It is pronounced as LaTeX because it's Greek. Those are Greek letters. That so happens to look like TEX, but it's not TEX. It's tau epsilon chi. Okay. And to republish everything, I wrote a script already, so it just goes through the whole process, to recreate the HTML document and then upload it to the server. And now when I refresh, dun dun, all done. Yes. Yep. But I hate to have wrong notes.
Yeah.
So being able to fix it as I spot those software. Or you can just white out the vertical line.
No, I'm a perfectionist. I can
Yep.
Did you say the script was it?
Huh?
What did you say the script was it?
The script
Yeah.
is LaTeX. The typesetting language is called LaTeX. LA tau epsilon chi. Better known as latex, but yeah. All right, so this side now starts with 1, right? Because if you plug in -1 as x, then the minus 2 times -1 is 2. 2 minus 1 is 1. Okay, if x is -2, you get 3. If x is -3, you get 5, and so on. So what I'm doing, what f is doing, is mapping all the non-negative integers to even numbers. 0 becomes 0, 1 becomes 2, 2 becomes 4, 3 becomes 6, and so on. All the negative integers are mapped to odd numbers. Okay? -1 becomes 1, -2 becomes 3, -3 becomes 5, and so on. Is that making any sense? Okay? So if that is the case, then when you look at the function, is it a function? Okay, what makes a function a function? Does it map everything in the domain to something in the codomain? Is there an integer where it doesn't know how to map to the codomain? Give me any integer, right? Give me any integer x, and I can evaluate this and tell you which natural number it maps to.
-2.
Huh?
-2.
-2, okay? If x is -2, -2 is greater than or equal to 0 is false. We go here, -2 times -2 is 4. 4 minus 1 is 3. 3 is 3 is a natural number. It is in the codomain, no problem. Okay. Is it injective? Which means, does it map each integer to a different natural number? That is what it's asking. So if you shake your head, then you have to tell me which 2 integers are mapped to the same natural number by f. Huh? 3 and -2?
Yeah.
Okay, so let's look at, we know what -2 maps to, right? -2 maps to 3 itself. 3, if x is 3, 3 is greater than or equal to 3 to 0 is true, so we just multiply by 2. So 3 maps to 6. 6 and 3 are different, so it doesn't, it's not a counterexample. Cannot prove the theorem wrong. Yep. 0 and -1. Okay, so let's check those two out. If x is 0, 0 is greater than or equal to 0 is true. 2 times 0 is 0. So 0 maps to 0 itself. What is the other one? -1. F of -1. -1 is greater than or equal to 0 is false. We go here. -2 times -1 is positive 2. 2 minus 1 is 1. So -1 maps to 1, which is not the same as 0. So that is not a counterexample here. So we can spend all day here to try to come up with counterexamples and would not be able to find one because the function is actually injective. How do we prove it is injective? Just because I say it is injective? Huh? Well, there's no such thing as minus infinity to positive infinity. So you use the technique called proof by contradiction. Okay? So this is not the place to show proof by contradiction, but it is important to kind of mention it because, in this class, not like, most textbooks where they have a dedicated chapter on proof techniques. In this class, I sprinkle, proof techniques, kind of all over the place because, whenever it applies, we'll say, oh, this is proof by contradiction. So you have repeated exposure in different contexts of how to use proof by contradiction. Okay. So this is proof by induction. So the idea is, in proof by induction, you assume the theorem to be false. In other words, if the theorem says f is injective, then you say, what if it is not? Okay? You negate the theorem. The very theorem that you try to prove, you negate. You say it is false. Okay? Okay? So in this case, I claim that f is injective. So the opposite of that is it is not injective. Okay? Then you think about, okay, if a function is not injective, what does it really mean? Oh, it means there is at least one possible case where if I pick two different elements from the domain, through f, they map to the same thing in the codomain. That makes the function not injective. Is that okay? So now the question is, can we prove that that assumption leads to disaster? Okay, because if the negated theorem leads to disaster, which we call contradiction in logic, then it proves that the theorem itself has to be true. Is that okay? So just by casually looking at this, okay, I'm going to use the tablet for this purpose. Okay. So let me scroll up a little bit. Oh, maybe a new page. There we go. So we're basically saying, what if f is not injective? Okay. If f is not injective, then we should be able to find. Okay. Any questions I can answer back there? Yep. Go ahead.
So in your notes, it's you're doing something different from what's in the right?
I think the notes is.
Because I remember I was reading about something called proof by cases, which is what now looks like to me.
Yep.
Yeah. Whereas proof by contradiction would be like.
Yeah, this is more of this is a direct proof.
Yeah.
Yeah, but I'm using proof by contradiction, just so they both work. So if f is not injective, then we are basically saying there exist two elements x, y in the domain. In this case, the domain is the set of all integers, okay, such that f of x is the same thing as f of y. This is the direct consequence of the theorem being false. Is that making any sense? If f is not injective, then this has to happen. I have to be able to find at least two different elements from integers so that f of x equals to f of y. They have a collision. Okay. So let's see how this cannot be the case. Okay, but this will still be separated into at least two cases. So the first one is when x and y have the same sign. Okay, x, y, same sign. And then the other one would be x and y do not have the same sign. Different signs. Okay. This one is easier because if they have different signs, I know one would be a odd number, the other one's going to be even number. And having an odd number to equal to an even number is a contradiction. It cannot happen. Is that okay? So are we convinced that this leads to a contradiction? Pretty much right away because of the way we define how they map. Is that okay? All right. So what if they have the same sign? If they have the same sign, then we rely on algebra to solve this problem. It's just plain old algebra. So what do I mean by just plain old algebra? We look at the way we define the function. So when they have the same sign, let's just say that they're both positive or non-negative to begin with. Okay, so it's 2x. So we further break this up into two cases. This is positive sign, this is negative sign. Is that okay?
Yeah.
Oh, okay. There we go. Sorry. So if they are the same sign, then we can say they're both positive or non-negative, or they're both negative. If they're both non-negative, which is the left branch, then we are basically saying, you know, x does not equal to y, but somehow 2x does equal to 2y. Can that happen? We know x and y are different. Why? How do we know it? Because it is the premise. X and y are different. And I forgot to mention that, so I'm going to put a note here. X does not equal to y, and they map to the same element on the other side. But do you guys agree that this is a contradiction, or do we have to prove that it is a contradiction? You want to prove it? Okay. Now, the word but in English is really the same thing as a conjunction. Now, this is really important because every time we use natural language, sometimes we can pick out the logical operators really quickly. When we use and, or, and not, you know, those are exactly the same way we use those operators in programming. But when you use the word but, it really means the same thing as and. Okay? Just quoting from our example in the previous class. Rich but not smooth. That but is really saying rich and not smooth at the same time.
Wait, what? Rich but not smooth at the same time.
Smooth, okay, rich but not smooth.
Okay.
Compare that to rich and not smooth. Do they mean the same thing? In this class, they do. In an English class, your professor will say, but the emphasis of the contrasting property is lost when you use the word and. Well, that's an English class. That's something that they have to deal with in English, not in this class. We don't really care about contrasting stuff.
So if we tell our English teacher.
In your English teacher, in an English class, if you replace all the words and with this symbol, see what's going to happen.
Professor's going to go bonkers.
Okay, so now we want to see, okay, why is this going to lead to a problem? Okay, now just this guy here, okay, do you think 2x equals to 2y if and only if x equals y? Just looking at this part, forget about x and y are different early. If I just look at this equation of 2x equals to 2y, can I divide both sides by 2 and conclude that x equals y just using regular algebra?
Yes.
Yes.
Yeah.
So the derivation of this gives me something like x equals y, but x is different from y is also given to us. So now we have a contradiction because they cannot both be true at the same time, which means this conjunction is false. If the conjunction is false, we have a contradiction. It is always going to be false. Doesn't matter which x or y you pick, this simply cannot happen. So we can do the same thing with the negative side. So on the negative side, it is negative 2x minus 1 equals negative 2y minus 1. But if you use algebra, the first thing you do is you add 1 to both sides, so they become negative 2x and negative 2y, and then you divide both sides by negative 2. Then you end up with x equals y again, which will again contradict what is given to you, that x is not the same thing as y. And once again, you arrive to contradiction. So this is proof by contradiction. Okay? So we'll get to a much more formal introduction to proof by contradiction later. But this is a quick and, it's just a quick and dirty way to get introduced into proof by contradiction. Are there any other classes that talks about proof by contradiction? I would assume the answer is yes, because it's a pretty common proof technique. No? Linear algebra? Okay. Probably not so much in calculus, but no, even in calculus.
Yeah, there's one professor I know. I'm not making this up. There's another professor I know.
I think even in calculus, you can use proof by contradiction. The stuff about the midpoint theorem and stuff like that probably can utilize proof by contradiction. All right, so that's the pine needle. Okay, the pine needle is the proof technique. Are we using a direct proof, which is what I'm doing in the notes, or are we using a proof by contradiction, which is what I just did in class? Okay, both work really well in this case. That's pine needle. We take a step back, look at the pine tree. What is the pine tree? The pine tree says F is injective. Is that okay? Now, injection is cool and good, but it is much more helpful if something is injective and surjective at the same time. So now can we say it is surjective? Now, what is surjection? What does it take for a function to be surjective?
Every element in the codomain must be mapped to.
Yep, everything in the codomain must be mapped to. Okay, so can we prove that with this F? Everything in the codomain, which is the set of all natural numbers, are mapped to from at least one integer. Okay. How do we prove that? Well, you can flip it, right? So right here, if x is even, okay, if f, this is the result of after you apply f, okay? So after you apply f, you say, okay, x is even. Can we go back to the integer that maps to x when x is even? The answer is yes. Because if x is an even number, then x divided by 2, that integer maps to x as a natural number. Is that okay? What if x is an odd number? Well, if x is an odd number, this has to be reversed as well, because we have to add 1 first, and then we divide the whole thing by negative 2. So let me fix that too, because since I already have the page opened up. So just bear with me when I do this. I'm looking for some words that maps to x. Okay, maps to x. Maps to. What am I missing? X is odd even, it is odd.
Maps to x.
Huh?
In the other period at the end. Maps to x.
Okay, maybe I can look for another one. There we go. So the inverse function is defined here. And this is how I type something over something. It's using a fraction. So the first part is the numerator, the second part is the denominator. But whatever, each part is surrounded by curly braces. And this is way before C and C++, by the way. Okay, so we fix that sign. And then we just republish the whole thing. And, oh, we fixed one but not the other one. Because there's another one down here, the ternary operator. Okay, we'll fix that too. Okay, we know it's injective already. So this is the other one. One more time. There we go. Okay, so now f is, we're defining f inversed, okay, because we kind of knew we could somehow show that f is surjective, because f is now injective and surjective. There's an inverse function for f, and the inverse function in this case is just defined exactly like this. Okay, well, let's figure out what it means. So this time, because it's an inverse function, it is mapping from natural numbers back to integers. Is that okay? Because the function versus the inverse function, they reverse the domain and the codomain. Okay. So I take x as a natural number. We know it's not negative, but we want to know whether it's an odd number or an even number. If x mod 2 is 0, it means it's an even number. If x is even, we just say, oh, okay, we'll map it to the integer of x divided by 2, which is going to be non-negative. Okay? If x mod 1 is not 0, which can be only be the other one, which is 1, that means x is an odd number. If x is an odd number, then what I do is I first add 1 to x first, and then divide it by -2. So that means the first odd number, which is 1, is mapped to -1, the first negative integer. Is that okay? So that's how we define the inverse function. Oh, so because it's injective and surjective, it means it's bijective. Okay? If it's bijective, what do we know about bijection in terms of the cardinality between the domain and the codomain? They have to be the same. So because we can find at least one f that is bijective, that maps between these two sets, the set of all integers and the set of all natural numbers, we know that these two sets have the same cardinality, which is aleph no. Is that okay? So this is really kind of odd because one is the proper subset of the other one, and yet they have the same cardinality.
So this is going back from, this is going back to the value that you're mapping from, right? This function is just going back to the
Yes. So all of this discussion in section 3 is using the same f. In other words, f is always defined like this in the entire section 3, but f inversed, which is supposed to reverse f itself, is this one.
Okay, so it's just
Yep. So are we doing okay so far with section 3? Are we convinced that the cardinality of integers is the same as the cardinality of natural numbers? Are we good? Because it's really odd, right? It's really odd that one is a proper subset of the other one, but yet they have the same cardinality. So the cardinality of f in this case is infinite, but it is also called countable, okay? Because anything that has a cardinality of aleph no is infinitely countable, which is kind of strange, okay? It's really kind of nice and strange at the same time, okay? So what else is countable? Let's look at this one. This one is kind of odd, because what we're going to do is we say, we'll look at all the two-dimensional coordinates using natural numbers, okay? So you're using a two-tuple to represent one particular location. The first item and the first item of the two-tuple, they both have to be natural numbers. Well, is that new to us, in computer programming?
Maybe.
Well, it should not. what is a pixel? How do we know which pixel we are talking about? It has a coordinate, right? But typically, I'm not saying in all cases, where is 0, 0 on the screen? Usually it is mapped to the upper left corner of the screen. And if I move to the right by 1 pixel, what is changed? Which part of the two tuple changes? The first one, the x coordinate changes, right? If I move down, it is the y coordinate, which is the second item of the two tuple. So we are pretty familiar with that representation. Yes?
I was going to say, it does how the graphics cards, hardware works when it takes in the data and puts it in that type of formation. So
Eventually, it has to turn into that kind of,
I'm just saying that's the algorithm they use for the
There's multiple levels of abstraction involved with graphics cards and
Yep.
processing.
At the raster level, yes.
At some point
At the last part of it, it becomes rasterized and it becomes individual pixels. Yes.
okay, so that makes sense.
Yeah, because when you ask me that question, how many people read up on the MBTI stuff, the personality type thing? Few, okay. So I'm an INTP, so it's natural for my mind to branch off. So when I heard the question, my mind just kind of do all the branching, or it splits into multiple multiverses. And then when I talk, it's sequential, right? So I have to pick one of the threads to verbalize, and I was having a really hard time picking which branch to verbalize.
I guess so.
Okay, so getting back to this stuff. Okay, so we know what a two-dimensional coordinate is, okay, because we use it to designate which pixel we use on the screen, two-dimensional. So I'm now going to claim that the space of two-dimensional coordinates, when you use natural numbers, has the same cardinality as natural numbers. Okay. In other words, there's a way for me to fold two-dimensional space into the natural number line. Okay. So how it doesn't make sense, right? When you think about it in an intuitive way, it just doesn't make sense, because if you pick any row on the screen, especially when it's a theoretical screen, each row of a theoretical screen goes on forever. It by itself is the natural number line. If you take any vertical line and look at it from top to bottom, it by itself is also a natural number line. So how can I take an infinite two-dimensional space and say, oh, we can fold it into one single line, and that is the natural number line. And they have the same cardinality. The cardinality of pixels in an infinite 2D space is the same as the cardinality of natural numbers. That's what I'm claiming. So let's figure out a way to do it, okay? So to do this, there's a quick and easy trick, okay, where this format really helps, okay? So what we're going to do is we'll draw the axes first. Okay, so we'll call this y, and we'll call this x, and I'm going to use intervals that are easier to read. So every 3 squares is 1, like so. So 0, 1, 2, 3, 0, oops, I take it back. I take it back. 0, 1, 2, 3, 0, 1, 2, 3. I mean, it's only off by 1, okay?
See, then what's that? Go to your boss and ask him about that whole number.
Yep. Okay, so if you pick a random dot somewhere, okay, you can tell me what the two-dimensional coordinate is, right? So if I take this one here, what is the coordinate of this dot here? It's 3, 2, because 3 is the x-axis. We say that first as a first item of the 2 tuple, and then the y coordinate is 2, so that becomes the second item of the 2 tuple, is 3, 2. Okay. So now I need to number all of these pixels in a way that is infinitely extendable. Okay, if you have read the notes already, there's no big surprises. You go like, yeah, we know the answer already. But since most of you have not read the notes, I can actually tell in Canvas. I haven't really searched for that yet, but I can pick on any item, and I can see who has clicked on it and who has not clicked on it.
You see my name, right? I hope you see my name.
But I don't really care.
Oh.
I don't really care in the sense that the quizzes and the final exam is based on competency. If you know this stuff prior to this class, you don't have to study. Okay, I'm not going to make people study just for the sake of studying. If you don't study and you ace the exams, hey, you deserve the grade that you get. On the other hand, if you don't study and you get a really poor grade, you also deserve the grade that you're getting. It is not my grade. It is your grade. And no, I do not use performance of my class as a way to evaluate myself. That doesn't work. Okay, so this is the way I number these things. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. I have to. Okay, I think 11, 12, 13, 14, 15, and so on. So what am I doing here? I'm sweeping, right? But the way I'm sweeping is diagonal. So I start with 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. Okay, I missed one number. 10, 11, 12, 13, 14. Details. Okay, so 10, 11, 12, 13, 14, and then we get to 15 here, and so on. So, do you think this approach is going to work? Yep. But remember, this space is infinitely large. I mean, if you think about in this direction, it can go forever. Okay? So now the question is, if I specify a particular coordinate, if I specify two coordinates, different coordinates, do they map to different numbers? Is it guaranteed? If I go to some space out there and I ask, what is the label of this particular pixel? Do I know it is going to be a natural number? Okay? Because this way it actually fills up the space, right? It fills up the space as far as you can go, it will fill it up. Is that okay? All right. But now we need a closed form. In other words, what we are looking for, okay, this time I'm using the function g instead of function f, okay? So I need a closed form where g is a function that takes a coordinate. And the coordinate has two components, the x and the y coordinate. And I want to say, I want to know how to define this g so that g is a function that maps from the Cartesian product of natural number and natural number to just natural number. I want to find out how to define this g. I can do it, just by, kind of filling up the diagonal lines, by hand. But that doesn't really work very well when I say, oh, what is the value or what is the natural number corresponding to the pixel at, 511 as x and 2016 as y. That would take you a long time to fill up those lines to figure out that one. So we want a closed form. We want an equation to do this. Does that make any sense? Okay. So we're trying to figure out what is G. What do you think? Now, one thing you can do is to read the notes. The notes actually goes through the whole process, the rationale and all. Okay. But the other thing is, we'll just go ahead and work with this. One thing that separates effective and productive programmers from not so productive programmers is, can they see patterns? Okay, can they extract patterns? So what do you see as patterns here? This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is going to be 15, and so on. So when you look at the numbers on the x-axis, what do you notice? So don't even look at all the other pixels. Just, okay, let me isolate what I want you to look at. Just look at this sequence of numbers. What do you notice? The difference is incrementing by 1. Okay, so very good. Okay, so we kind of noticed that, right? So the difference between 0 and 1 is just 1, but the difference between 1 and 3 is 2. The difference between 3 and 6 is 3. The difference between 6 and 10 is 4, and so on. So we kind of guess the next one is going to be 15 plus 6, which is 21, and then 21 plus 7, which is 28, and so on. That's not a bad way to start, guesstimating how to do this. Okay. So that makes me think that the base, okay, we don't really care about all of the other pixels, but if you look at everything that has a y coordinate of 0, okay, the way we look at the values that spread out on the x-axis is going to be like this, okay? So we kind of come up with this suspicion, okay? So we say, we just know what x is, but the y coordinate is already a 0. We just want to do this, okay? Because, at this point, this is all we want to focus on, is we put a constraint on ourselves and say, okay, let's not take y into consideration. We're only looking at all the numbers along the x-axis, because it seems like we got a pattern here. And the pattern seems to be something like this: 0 plus 1 plus, what is it again? 2, 0, 0, 1, 2, 3, 6. And then 10, and then plus 4, plus 5 is 15, and so on. Okay? And what is x going to determine? X is going to determine how many terms we're adding. Okay? Okay. Not all the way to x.
Well, but I mean, it's not 1 plus 3 plus 6. Like the fourth, like x for 4 isn't.
When x is 0, when x is 1, when x is 2, when x is 3.
Yeah, but you're not. You shouldn't be summing all.
Oh, you should. Yeah, well, you shouldn't be summing that. Okay. Okay. Back. Okay. So we want those numbers. And how do we get that? 0 plus 1 plus 2 plus blah 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 up to x. Okay, so we'll check whether that works or not, right? So we ask the question, what is G? Oh, okay, just crapped out. Okay, so that's just 0. G of 1, 0 is 0 plus 1, okay, that's 1. G of 2, 0 is 0 plus 1 plus 2, which is 3. G of 3, 0 is 0 plus 1 plus 2 plus 3, which is 6, and so on. So is it working? Yep, go ahead.
So the pattern is that since that's 0, that's 0, that's 0, and then that's 1 plus 0 is 0, then that is 2, that is 1 plus 2 plus 0 would be 3, and then 3 plus 3 plus 0 is 6.
0 plus 1 plus 2 plus 3 is 6. So we keep adding until we get to x. Okay. So if we look at some, x again, okay, just some random x value, is there a better way to write it instead of spelling out 0 plus 1 plus 2 and all the way up to x? We can use sigma, the summation. I starts from 0, it ends at x, and we're just adding i's. Is that okay? So we are, instead of spelling out the entire series, we're just using the sigma notation and go like, okay, this is the format, this is the loop to do it. For I equals to 0, I is less than or equal to x, keep adding I to the sum. Is that okay? But then we go like, well, this is kind of cool, because instead of using this kind of long format to do it, but how do we turn this into a single or a few fixed operation in arithmetic so that we don't have to keep adding stuff? This can be done with a loop, but a loop is expensive. We want to turn this into just a fixed number of arithmetic operations, so it can be done like that, regardless of what x is. So how do we do that?
Y is equal to kx plus b.
But how do you come to that conclusion? Okay, so now our focus is a little bit different. Our focus now is to say, how do we turn this into a closed form? Now, I know you guys can look it up, and I know some other classes have already introduced the solution to this. But my focus is not that. Things you can look up, you can just look up. But if this is the first time you see something like this, how do you work it out so that you can find the pattern, so that you can find the closed form of this thing? The first thing you do is observe. Okay? Yep.
Is that y on top?
It's x. Just bad penmanship there. That's x. Okay? So you say, okay, when x is 5, okay? When x is 5, then this is, this thing becomes 0 plus 1 plus 2 plus 3 plus 4 plus 5. Okay? And when x is 6, okay, we'll just analyze these two. I know we are running out of time, but I do want to end with this so that at least we can think about this a little bit. So what we notice is if you add the first item to the last item, it is the same as the sum of the second item and the second last item. The third item versus the third last item add up to be the same. Okay? 0 plus 5 is 5, 1 plus 4 is 5, 2 plus 3 is 5 as well. But how many 5s do we have? Approximately 5 divided by 2, because you're basically pairing up the items, right? So how many pairs do we have? The number of items divided by 2. But sometimes that doesn't work out, because when x is 6, then we have 7 items. So when we have 7 items, what is going on? 0 pairs up with 6, so the sum is 6. 1 pairs up with 5, the sum is 6. 2 is paired up with 4, the sum is 6 as well. Then we have a 3 left over that is kind of on its own, not paired up with anybody. Then it is by itself. But that turns out to be x divided by 2. Okay? But so it's kind of cool in a way. We can now say when x is odd, we can use one way to do it. When x is even, we use the other way to do it. But I hate the ternary operator, as you guys do. So now the question is, can we somehow unify these two patterns and use the same closed form to express the result? Okay? That is where the notes is going to take you. Okay? Because the notes will start with this observation and say, well, when x is odd, we can have this closed form. When x is even, we can have this closed form. Okay? So we use a ternary operator. And then in the notes, I will manipulate the summation until the summation of both the odd and the even look exactly the same. Then we can say, oh, toss away the ternary operator, because the then and the else are exactly the same. So over the weekend, I want you guys to read ahead of me and try to finish the entire module for Aleph No over the weekend. and work on the function homework assignment is due in a week. I'll see you guys in a week, in 5 days, and have a nice weekend. And next time.
I just want to go to your office hours because I'm not feeling well. I can barely stand up.
Okay.
I'll talk to you about it.
Well, then you can.
Yeah.
Okay.